Hello everyone, welcome to my channel Chem Insider. In today's video we will be discussing about the very important topic of chemical bonding, that is hybridization. The topic of today is hybridization. In the previous video we had learnt about the explanation given by the valence bond theory, that is by the scientist Pauling and etc. What they explained was, even though the explanation was given by Sidwig and Powell, Pauling further clarified certain doubts regarding the hybridization. If you had remembered, in the previous video, I said a particular topic when we were discussing about the overlapping of atomic orbital. That is, when you consider for a CH4 molecule, the three p orbitals, the px, py, pz orbital, were lying perpendicular to one another, which resulted in the orbitals should be forming a 90-degree bond angle, and thus clearly ruling out the tetrahedral bond angle of 109 degree 28 minutes. Therefore, Pauling proposed certain hybridization concept which was useful in order to know the exact geometry of given molecule. So, what he said was, whenever you consider the atomic orbitals of a molecule, it gets hybridized with respect to the atomic orbitals of the own self and overlapping, thus resulting in several different hybrid orbitals. Like for example, if you consider CH4 molecule itself, if you consider carbon in CH4 molecule which has the electronic configuration 1s2, 2s2, 2p2. This is in the ground state. But in the excited state, one of the 2s electron present in the 2s orbital, gets excited to the p orbital. So, if you write down the atomic orbital of that particular 2s to p, so there will be 4 electrons each in 1s and 3p orbitals. So now, he said that since the electron can be jumped from one position to the other in the excited state, these two orbitals, that is the s and p orbitals, will be having same energy. Therefore, Pauling explained that the atomic orbitals which have almost same energy might get hybridized to one another to form equal number of hybrid orbitals. Even though in this case of s and p, if you consider s orbital and p orbital, even though they have almost same energy, they will not be equivalent. Therefore, Pauling said that the 1s orbital of 2s and the 2p orbitals get combined with one another, that is in the form of intermixing with one another, to form 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals which are useful to relate in the geometry of a given molecule. So, how is that possible? For that particular condition, he gave away 4 salient features of the hybridization and 4 necessary conditions for atomic orbitals to undergo hybridization. First, will let us know about the salient features of this hybridization concept. So, what is this salient features of this hybridization concept explained by Pauling? Salient features of hybridization. So in this, the first point he said that atomic orbitals of one atom, get overlapped with one another to form equal number of hybrid orbitals. Atomic orbitals of one atom overlaps to form hybrid orbitals, equal number of hybrid orbitals. That is, if you are considering 1 2s and 2 2p, if you are considering 1 2s orbital and 1 2p orbital, out of these three, if we are just considering 1 2p and 1 2s orbital, these two get combined to form sp hybridization, and they will be forming two sp hybrid orbitals. The first point is the number of hybrid orbital formed will be equal to the number of atomic orbitals being hybridized. If you are considering a 1 2s orbital and 1 2p orbital being hybridized, then you will be forming two sp hybrid orbitals. Okay, if 1 2s and 1 2p orbital is overlapping with one another to form hybridization, then it will yield two hybrid orbitals with sp hybridization, and these two sp hybrid orbitals will be having equivalent energy. That is the second point. That is, so whenever you form equal number of hybrid orbitals in a particular hybridization, those two will be having the hybrid orbitals will have equivalent energy. The hybrid orbital will have equivalent energy and same shapes. The hybrid orbitals will have equivalent energy and same shapes. That is, if you consider this is the energy of 2s, this is energy of 2p, these two get combined to form 2s, 1 sp, and this is one more sp hybrid orbital. 1 2s and 1 2p get combined to form two sp hybrid orbitals, and these two have equivalent energy. These two will be having equivalent energy. That is the second point, and further they will be having same shapes. Next, for the third point, if you consider for the atomic orbitals of pure atom, if you consider pure atomic orbitals and these hybrid orbitals, if you consider pure atomic orbitals, that is which we had discussed in the earlier video, the pure atomic orbitals of sp hybridization will be giving us 180-degree bond angle, but in case of sp3 it will be giving 90-degree bond angle. But if it undergoing sp3 hybridization, it should be forming tetrahedral geometry. Therefore, when you consider for the shape of a molecule, hybrid orbitals are more useful to explain the hybridization. Hybrid orbitals are more prominent to explain the shape of the molecule. Hybrid orbitals are more prominent to explain the shape of the or given molecule than pure atomic orbitals. Hybrid orbitals of a molecule are more prominent when compared to pure atomic orbitals in case if you are explaining the shape of the molecule. Therefore, hybrid orbitals yield us the tetrahedral geometry in CH4 molecule, but not the pure atomic orbital. And next, the fourth point is, if you are considering electrons present in the given orbital, hybrid orbital arrange themselves in such a way that they are away from the electron repulsion. If you are considering for the hybrid orbital explaining the geometry, hybrid orbital arrange themselves in the three-dimensional space in such a way that they are experiencing as low electron repulsion as possible. Okay, hybrid orbital arrange in space to experience as low as repulsion possible, to experience electron repulsion as minimum as possible. Experience electron repulsion as low as possible. Therefore, we can clearly say that hybrid orbitals form stable bonds when compared to pure atomic orbitals. So these are the four salient features of hybridization concept. That is, atomic orbitals when overlap with one another, they form equal number of hybrid orbitals. If 1s and 1p is getting hybridized, then it will form 2 sp hybrid orbitals. If 1s and 2p orbitals are overlapping, then it will forming 3 sp2 hybrid orbitals. If 1s and 3p orbitals are overlapping with one another, they will be forming 4 sp3 hybrid orbitals. Second point, and this particular hybrid orbitals which are formed by the hybridization will always have equivalent energy and similar shapes. And the third point, what these hybrid orbitals are useful for is they explain the geometry of the molecule more clearly than that of the pure atomic orbital. And in the fourth point, these hybrid orbitals arrange themselves in the three-dimensional space to provide a clear geometry and experiencing minimum repulsion. Therefore, they form a stable bonds when compared to pure atomic orbitals. So this is all about the salient features of hybridization. Next, the necessary conditions for hybridization. For the conditions of hybridization, there are literally four conditions which are to be followed for hybridization. There are four particular conditions which have to be followed in order to explain the hybridization of atomic orbitals. Those are, first one, the atomic orbitals should be of valence shell. The atomic orbitals should be of valence shell. The atomic orbitals should be of valence shell. That means the atomic orbitals of the valence shell can only undergo hybridization. If you consider for the carbon atom, it has 1s2, 2s2, 2p2 configuration, where hybridization takes place only from the 2s and 2p orbital, but not the 1s orbital. So therefore, atomic orbitals which are present in the valence shell will only be used for hybridization. The second point is, the atomic orbitals which are being hybridized should have almost same energy. The atomic orbitals should have almost same energy, that is almost equal energy, in order to get hybridized. For the atomic orbitals to get hybridized, they should almost have same energy, that is almost equal energy to undergo hybridization. Next is the third point. There is no requirement for electron to be promoted to their excited state. In some cases, what we observe is, for example, if you consider the carbon itself, there the electron gets excited to the 2pz orbital of p from 2s. In some cases, there is no excitation possible. Therefore, the promotion of electron, that is the excitation of electron, is not clearly necessary. Promotion of electron is not necessary condition for hybridization. That means if they want, they can undergo excitation. If they don't want, they cannot undergo excitation. That means the promotion of electron is not compulsory for undergoing hybridization. It may undergo excitation, it may not undergo excitation, and those compounds may also form hybridization. That is the third condition. And in the fourth condition, what we observe is, the orbitals should not be necessarily half-filled for undergoing hybridization. If we are considering the valence bond theory, where we say that orbitals should be, if you consider the covalent bond theory, that is of Koechlin and Lewis, where we said that half-filled orbital overlap with the other half-filled orbital to form completely filled orbital. But in this case of hybridization concept, there is no requirement for the atomic orbital to be of half-filled to undergo hybridization. It may also undergo hybridization even those electrons are completely filled in the orbital. Okay, so half-filled, not just half-filled, but completely filled orbitals can also undergo hybridization. not just half filled but completely filled orbitals also undergo hybridization. That is, not just half filled orbitals should be undergoing hybridization. Completely filled orbitals can also undergo hybridization according to the hybridization concept of Pauling. Okay, so these are the 4 conditions which an atomic orbital has to follow in order to form a hybridization concept. Now, let us discuss about different types of hybridization. There are several types of hybridization, but the basic one is those which involves s and p orbital. Usually, the most of the molecules or compounds in environment is of s and p hybridization. That is, which hybridization involving either s and p. Okay, so there are particularly for the sp hybridization, that is the s orbital and p orbital hybridization, we have 3 types of it. Those are sp hybridization, next is sp2 hybridization, and third one is sp3 hybridization. Even after this, we have furthermore different types of hybridization which involves d orbital also, but we'll first discuss about the 3 basic hybridization concepts which we come across in our day-to-day chemical chapters. So, first one is sp hybridization. So, sp hybridization is, for example, whenever you consider one s orbital and one p orbital of a valence shell. If you consider one s orbital and one p orbital of a valence shell, they may get overlapped with one another to form a 2 sp hybrid orbitals. For this particular condition, the majority of this particular reaction happens only if p is in the pz direction. Okay, if the p orbital present is in pz axis, then the extent of hybridization is more stronger when compared to the orbitals which are of px and py. Usually, the sp hybridization takes place with the p orbital in the z-axis. Okay, so what happens in this case is, if you consider this as the coordinate axis, let us say this is the z-axis, x, and we have y towards u. So now the s orbital, which is of the spherical shape, for example, we are considering here is beryllium chloride. So here beryllium has electronic configuration 1s2, 2s2. Okay, beryllium has electronic configuration 1s2, 2s2, that is in the ground state. When it gets excited, it forms configuration 1s2, 2s1 and 2p1. In the excited state, it undergoes 1s2, 2s1, 2p1 electronic configuration. So clearly, it involves 1 2s and 1 2p orbital to undergoing sp hybridization. Therefore, it forms 2 sp hybrid orbitals. So now, how is this hybridization going to take place? Now, if you consider the s orbital, that is the 2s orbital of beryllium, and the p orbital, as I said, we are considering the p orbital in the z-axis. Okay. So this is the p orbital, which has positive in this direction and negative in this direction. For s orbital, it is always positive in all the directions, right? Now just consider this as a simple mathematical addition. So what happens here? When you take this s orbital, which is of the positive charge in all directions, and place it exactly on this particular orbital. So what happens here? The positive and the positive gets added up, right? Plus gives more value. Like if you consider this is plus 2 and this is plus 3. Plus 2 plus 3. If it is plus 3, this will be minus 3. This is just a simple mathematical addition. So now I'm just considering the half side of this z orbital. So now if you just consider this half, so this is plus orbital because it is always positive. Plus and plus get combined to form a huge orbital such as like this. Okay, if this is the x and this is the z-axis. Plus side and the plus side get combined to form a huge plus, that is plus 3 and plus 2 gives plus 5. Now plus 2 on this side and the minus 3 on the opposite side get cancelled to give minus 1. Therefore, the negative orbital of the p of sp hybrid orbital becomes smaller one. Okay, are you getting this? So what happens here is, this particular s orbital is spherical and symmetrical in all directions with a positive charge. So if you take the positive charge in a spherical form and place it on the origin of the p orbital, positive end and positive end get added up, that is plus 2 gets plus 5. In case of this, which is on the left hand side of the x-axis, minus 3 and plus 2 get cancelled out to form minus 1. Therefore, the sp hybrid orbital has one bigger lobe of positive charge and one small lobe of negative charge. Okay, this is one sp hybrid orbital. That is, this is one type of sp hybrid orbital, and in the other case, the same pz orbital will be of opposite direction. That is, plus on this side and minus on this side. Okay, plus on the left, minus on the right. Then it will give us different type of hybridization. If this is z and x, the p orbital with positive charge will be greater on this side and smaller on the other side. So this is one sp hybrid. This is one sp hybrid orbital. This is the second sp hybrid orbital. Okay. So now, if you consider for beryllium, which has two sp hybrid orbital, it will be of the structure such as like this. So first one with a smaller charge. So let us write this as here. Okay, this is the positive, this is the negative of the second sp orbital. Now for the positive one of the other side, this is the other one, this minus and plus. So the axis slice is, this is x-axis, this is the z-axis. Okay, so these are the two hybrid orbitals of sp. So if beryllium undergo sp hybridization, it will have one hybrid orbital which is in the yellow on the left hand side when the positive charge of the pz orbital is on the left side. If the positive charge of the p lobe is on the right side, then it will form the lobe which is in the form of pink color. Okay, so this is how sp hybridization takes place. So if you clearly observe over here, now the chlorine's pz orbital on either side gets overlapped with the sp hybrid orbital of beryllium to form BeCl, Cl. Okay, so this is how beryllium chloride forms the sp hybridization. So when beryllium chloride, if you consider for the sp hybridization, we have S character and P character equal, that is S character is 50% and P character is 50% in the sp hybridization. So if we consider sp hybridization, it will have equal S and P character, that is a 50-50%. Okay, so this is how sp hybridization takes place. In the next class, we will be discussing about sp2 hybridization, sp3 hybridization, and some other examples of sp and sp3 hybridizations. Okay, this is all for today. I hope you have understood this particular sp hybridization concept. We will learn more about the sp2 and sp3 in the next class. Thank you for watching.